Welcome back, folks. Still working with phasers. You're not sick of them yet, are you? I hope not, because we're going to use them a lot. A few videos ago, I said, well, we're going to be forced to use differential equations if we don't come up with a clever way to get around them. And here's the beginning of how we get around them. Everything that we do in circuit analysis comes back to KVL, KCL, and Ohm's law. Ohm's law works for a resistor, but when we move to phasers and when we're working with capacitors and inductors, we can't use Ohm's law, okay? Unless we do something clever. And here's the beginning of doing something clever. We have to relate the voltage and the current across and through all of these components in the same way, and we're going to do it in a way that resembles Ohm's law. So we're going to rewrite Ohm's law. Isn't that fun? You get to rewrite a fundamental law as V equals I Z. Okay, and Z is going to represent our impedance. And impedance is just the complex relationship between a phasor voltage and a phasor current through any of these components. But we got to figure out where they come from. I don't like it when things come out of nowhere. So we're going to do a little bit of math so that we can see where these impedances come from. But we're going to use this form of Ohm's law. It turns out you've been using it. You just didn't know you've been using it because we didn't deal with capacitors and inductors in the same way. And then to pay homage to one of my old professors, he liked to fondly refer to this as super Ohm's law, which is completely made up, but he's a really good professor, so give me a moment to just think about the days working for him. So I think he was the first person I graded for in grad school. And then I took over his class. Okay. Anyhow, so super Ohm's law, we got to make it work. Now I'm going to break this into 3 videos. There's a little bit of intro on this one. There's going to be a little bit of outro on the third one, but I'm going to deal with the individual components. I'm going to start with a resistor. It's going to feel silly with a resistor because we already know what the solution is going to be. We are then going to move to the inductor and capacitor, or capacitor and inductor, I'm not sure the order, and do the same thing. So I'm really starting with the resistor in this video just so that you get comfortable with what I'm doing on a component that we're already familiar with. Okay, so let's do that. Let's take a voltage supply, and now this is a AC voltage supply. So it gets that funny little symbol that looks like that. We get that squiggly line that looks like a sinusoid, but it still has a polarity. So you're going to get a plus and a minus on either side. Let's take that voltage supply and put it across a single resistor just like this. Okay, it's going to have some value R. We're interested in the current as a function of time, and this voltage supply has some voltage as a function of time. Okay, what we want to do is place a sinusoidal voltage across this. So it's going to have an amplitude of A. It's going to be a cosine. It's going to have some frequency omega, which is in front of t, of course, and some phase shift theta, and that's going to be in volts. So we're going to take that voltage and we're going to put it across this resistor, and then we're going to try to figure out how the current comes out, and we're going to try to get it down to a complex number that represents the relationship between the phasor for the voltage and the phasor for the current. Okay, so let's see. If I want to find this current, like I said, this one's going to feel silly, but it's going to lay the groundwork for the next 2. If I want to find that current, I have to use Ohm's law, right? So the current is the voltage divided by the resistance. Okay, so I can plug that all in and say A cosine omega t plus theta. That's in volts, and I'm dividing by R. So nothing too crazy there, but now I have an expression for the current. I have an expression for the voltage, and I have an expression for the current. So if I want to put these together and I want to say, okay, what is the voltage over the current, right? And that's going to give me my impedance, because I'm ultimately interested in the ratio between those two. I want to relate those two. That's what Ohm's law does, and that's what impedance is going to do as well. Okay, so we can, let's see if we can cut and paste some stuff just to save my carpal tunnel just a little bit. Let's try to do it right the second time. Come on, pasty program. Okay, so we can drop that down there. That's our voltage, right? And here's our current. Okay, so a few things drop out right away. We can see that we have cosine omega t plus theta in both of these. So that's going to drop out. Ready? Let's drop that out and that out. One's in the numerator and one's in the denominator, and we're left with A over R. Okay, so we have A in the numerator and A in the denominator, and that's going to leave us with 1 over R, which is, of course, equal to R. Okay, I told you it was going to feel silly for a resistor, but this is the process we're going to follow. We're going to take a known voltage, we're going to put it across the component, we're going to find the current, and then we're going to take the voltage divided by the current and work our way towards phasors if we can, which we can, and figure out what the impedance is. So the impedance of a resistor, okay, Z sub R, if you want to call it the impedance of the resistor, is equal to the resistance. So you've been using the impedance this whole time. You just didn't know you were using the impedance. Okay, so that's our big result for this video. Stay tuned. We are going to do the same thing. Let me go peek at my notes here. We're going to do the same thing for a capacitor next. It's going to look a little different. There's going to be a little bit of a wrinkle, but you'll do just fine. Stay tuned and good luck, folks.